Hey gang, for number 21, I might actually do this in a couple parts just because it's easier for me. So let me start with the first part. You have a ladder. Let's see, you have a ladder, it's 25 feet. Oops, sorry, I don't know why that's so blurry. You have a ladder, it's 25 feet long. It's leaning against a house. The base of the ladder is pulled away from the wall 2 feet per second. Okay, so they give you the picture here. Let me just draw it here. If it defocuses, I'll fix it. Okay, just hang in there with me. Now, remember when I was doing the lecture that I told you it's really important to be clear on what is fixed and what is changing. So the ladder is not going to change its magnitude. It's always going to be 25 feet. You know, it's not like sometimes going to be 25 and other times going to be 10. It's always 25. So you can put that in the general equation because it's always going to be 25 feet. What is going to change with time is that the ladder is being pulled away from the wall. Okay, the ladder is being pulled away from the wall at a rate of 2 feet per second. All right, so what is going to happen is that over time, the ladder is going to be pulled away from the wall so that this side is eventually going to get smaller and this side is going to eventually get longer. Because as you pull the ladder away from the wall, this side goes down and this side gets smaller and this side will get larger, and eventually the ladder will be flat on the ground. Okay, so what I'm trying to say is make sure you make this a variable and make sure you make this a variable, because this side will change with time and this side will change with time. Okay, how fast is the top of the ladder moving down the wall when the base is 7 feet? Okay, so remember, when you write the equation, it always has to come off of the general picture, the picture that's true for all time. So this is a general picture. You have a right triangle. You have the 3 sides. So you got to know what equation that is. So what are you going to use here for the equation? Okay, so hopefully you're thinking Pythagorean's theorem. That would be correct. So the equation that I'm going to use is Pythagorean's theorem. So x squared plus y squared equals to 25. And remember, when you do your derivative, it comes off of the general, right? It always comes off of the general, never the specific. So when I see students with problems, they're usually incorporating too much data and they're incorporating things that weren't referenced in the question. So it's really good to like stay to a minimum. It's just good to stay to a minimum. All right, so now when you take the derivative, make sure that you're taking the derivative in respect to t. Sometimes when we start this section, we're still thinking dy dx. We're not in dy dx anymore. Everything is a function of time, meaning that x changes with time and y changes with time. Okay, they're both these factors, these magnitudes are affected by time. All right, so everything's a chain rule. So as I take the derivative, I'm thinking chain rule. All right, so derivative of x squared. First you do the derivative of the 2. So that's 2x. And we never really write 1, right? Because that looks like a prime to us in calculus. All right, so that's the derivative of 2. And then the derivative of x is dx dt. All right, now the next part, you first do the derivative of the 2, so that's your 2y, and again, we don't write the 1, that looks like a derivative. And derivative of y is dy dt equals to the derivative of the constant is 0. Okay, so this is the derivative. I would suggest you clean this up a little bit, like divide everybody by 2. It just makes it like a little nicer. Less stuff floating around. Okay, so this is as far as I'm going to go at the moment for the derivative. I've got to be clear what my question is. How fast is the top of the ladder moving down the wall when the base is 7? Okay, so how fast is this side, the top of the ladder here, moving down the wall when the base is 7? All right, so the question is what is the rate of the y when the x value So remember now, this is a snapshot. We're going to be fixed in space because they're saying when x is 7 feet. This side's always 25. We don't quite know what this is yet. We'll figure it out. All right, so this would be what I call the snapshot, or the moment in time when you're freezing the movie. You're like freezing the movie here, right? The ladder's falling all the way to the ground, but you freeze it when x is 7. All right, so that's what we're looking for. We're solving for dy dt, right? How, let me find it again. How fast is the top of the ladder moving down the wall when the base is 7? Yep, all right. So we're solving for the rate of this side. So let's isolate what we're looking for. So let's isolate dy dt. So for me to do that, I'm going to move this term over to the right. Okay, so notice it's negative now because I've moved it over to the right. And I'm looking now for this part of this term. So I want to divide off the y. Okay, awesome. So now I have isolated what I'm looking for. Especially if you're going into computers, a lot of times they want you to isolate the equations because you're going to have the parameters at the top, and if you alter the parameters, you then don't have to fix the entire frickin' program, right? You just have to fix the parameters at the top. So it's really important that we can like manipulate equations, especially if we're writing computer programs. Okay, so now I've got this isolated. So the only thing I'm missing here is I just need to plug in these parts. So if you notice, I know what x is in the snapshot. I know, do I know dx dt? Did I not write that down? Let's see, that would be the base of the ladder is pulled away at a rate of 2 feet per second. Okay, we have to write that down. This is the base of the ladder. This guy is being pulled away. That's the rate. No, dt, Rachel, dt. dx dt. Now, remember, you have to figure out, let me just see the timing on that. Feet per second, okay. Now remember, you have to figure out whether this is positive or negative. And what determines whether this is positive or negative is if it's corresponding, like this is referring to x. So its corresponding part, or in this case x, is getting bigger or smaller with time. So with time, the x value is getting larger, so it means that this is positive. If for some reason the ladder was being pulled up and this was coming in this way, x would be getting smaller and then this would be negative. So the positive or negative depends on whether that particular part or factor is increasing or decreasing in magnitude with time. Are you taking away from that substance, or are you adding to that substance? Okay, that's the concept of what you're trying to figure out. All right, gang, so really the only thing I don't know now, I know x, I know dx dt. So the only thing I don't know right now is y. So for y, we're just going to use intermediate algebra pre-calc sort of concept, and you may already know this off the top of your head. We just have to figure out this value here. So we have to figure out y. So I'll work it out in detail, but you might know that. That looks like a familiar triangle, like one that comes up very often to me. Hold on a second. Brain is not. And we know what x is. X is 7 in this scenario. All right, so 7 squared. We said this was 25 squared. Okay, my brain saying that's 625. Okay, we subtract the 49 to the other side. 576. 24. Yep. Right, so we're taking the square root of both sides here. Yep, so this is a popular one. Some of you guys may have remembered it. All right, so in this particular instant, when this side is 7, this side is 24 feet. All right, gang, we're there. We can do it. So the last step here now is that you want to... Did everybody see? I don't know if I filmed that very well. Right, you're solving. So what we did here is we solved for y in the specific scenario. Okay, so we plugged in the value of x, we plugged in the size of the ladder, and we just solved out the y. We took the square root at the end. Okay, so that was solving for y. All right, so now the last step here is you want to plug in. And make sure when you plug in, you use the specific case or the snapshot. Okay, so when you do the plug-in at the very, very end, you're using the case where you know all the information, where you're sort of frozen in time. All right, here we go. This is the finale. And this is why I'm going to be doing this in 3 parts, because this one video is already super long. Okay, so we got to plug in x. X we said was 7. There's a minus sign in front of it from the formula. Dx dt we said was positive 2. I'm just going to be a little obnoxious with the signs, not to necessarily be obnoxious. I just want to make sure you always think about it. Y, the magnitude of y is 24. All right, so let me reduce here. 2 and 24, that's 1 and 12. So this is negative 7 over 12. Now, some people will do, like when you're doing chemistry, that dimensional analysis, they plug in all the units and then they cross out the units. I just usually reference what I know it's in. So everything in this problem is feet. So y is in feet and time is in seconds in this problem. So this y is in feet, t is in seconds. So it's negative 7 over 12 feet per second. Now make sure that makes sense. So does it make sense that this is negative? And it should, right? Because this side over time is coming down, right? This side over time is coming down. So that means that its derivative must be negative. All right, gang, that took me about over 12 minutes, but I wanted to explain it in detail. I know this is one of the more challenging topics. I know there's a B and a C. I'll get to that, okay? All right. The only difference between the other parts here is that they're just changing the value of x. So you're just going to change the variable. You know, the Pythagorean theorem will give you a different value. It's the same. All the calculus is the same, just the plugins is different on that. All right, gang, that's it on this one. I'll on part A. I'll catch you for part B. Bye.